The fourth of four stages in Piaget's theory of cognitive development is formal operations. Formal operational thought is the kind that we would expect from students who are somewhere between 11 years of age, give or take. Remember, we give or take with Piaget's theory, from there all the way through adult. And the defining characteristics are that they are capable of propositional logic, they are able to do scientific reasoning, we'll do examples of all of these, combinatorial reasoning, and finally this reasoning about probabilities and proportions. Now, for example, propositional logic. What we're asking students to do in this case, when we're trying to determine this as their developmental level, is we're asking them to suspend what they know to be true in order to entertain what we're going to give them as truth, or as tautological thought, or tautological concepts. So, for this example, we're going to say that we want you to suspend what you know about age and the relationship of these particular people to each other, and we'd like you to say that babies are older than children, that children are older than adults, and assume that those two are true. That being the case, is it true or false that babies are older than adults? If a child is formal operational, is able to sort of suspend what they know and can entertain other thoughts on the side, and then is willing to come back after that to what they know, but they can kind of live in this fantasy world for a minute, they're going to say that when we say, are babies older than adults, they'll say, yes, they are. They'll do that because they have reasoned that because the first two are true and I'm suspending reality, then it's okay for me to say that the third one, this babies are older than adults, that's true. The other example that you see down there is this, it's basically just an algebraic statement. And we would ask students to add in, or to replace these terms that we have, these abstract terms, with concepts. Formal operational thought, at its height, is really the idea that we can take something that is abstract and something else that is even perhaps more abstract and put them together to form something that is further out there, further abstract. An example that is frequently used is if we have a piece of music that's being played and we have a painting. We could say one of Monet's Water Lilies, and the music from the Pastoral Symphony of the Messiah. And we would say that music is the backdrop. That's the sound, that's the mood of this story. And the painting is the set. And what we ask the students to do is to create some kind of a story that uses those two things. And as you can imagine, the story would probably change quite a bit if we were to change from something that is peaceful and calm type of music to some music that's really raucous, or has a very heavy beat, or is maybe headbanger music, whatever. So we can understand that there would be a difference there. That is the product of formal operational thought. And that brings to mind one very important idea. And that idea is that when we're evaluating kids for formal operational thought, we really need to ask, why did you say that? What do you mean by that? Where did you get your ideas? Take, for instance, this scientific reasoning example. Forming and testing hypotheses is what they should be able to do. And we would ask them this question, for instance: why do hurricanes weaken as they move from the equatorial region north? And the answer to that is going to have several steps. The first thing that they're probably going to say is, from their experience, that they're going to believe that that's true. And then they'll start to figure it out. Well, okay, warm water feeds hurricanes, and it's warmer around the equator, and as we get further north, the water cools off some, so there's not as much warm water to feed the hurricanes, so it becomes weaker. And we ask them to explain that. Kids who are formal operational, even if they're wrong in their answer, they'll go through that process of thought. We have to be careful to separate content knowledge as much as possible from cognitive development. So if they have the reasoning process down, but they don't have the facts right, that's okay in this case. The final area we look at, or the third area, excuse me, is combinatorial reasoning. And what we're asking them to do is just to, again, answer these questions. If they do it just from sort of an algebraic formula standpoint, especially in this first one, well, actually in both of these, what we're going to end up with is fairly simplistic answers, and they'll answer them by saying, well, I got my answer because I took 4 kinds of meat, 3 kinds of bread, and 4 kinds of condiments, and so 4 times 3 times 4 gives me my number. The same with the statement below that, which is the 5 pants, 5 shirts, 4 ties, and 3 jackets. You know, that's more multiplication, but they would do 5 times 5 times 4 times 3, and they would come up with their answer that way. Again, whether they got the numerically correct answer, the sum or the product of all of that, or not is really not the issue. It's how did you get that? But think about this. Remember that it's possible that these folks are going to say, well, okay, you're assuming that I have to have one of each for that sandwich. What if I'm going to go with sandwiches that don't have any meats on them, or that don't have any bread, or only have 1 piece of bread, or I have lots of combinations of different kinds, and I can do my combinations in different proportions, and they may come up with literally thousands of possible sandwiches that can be made here. In the same way, we can talk about outfits, or they may say, well, you know what, I've always heard that I'm a guy, and since I'm a guy, the answer is going to be 0 because guys don't wear outfits. So it may be that they completely skirt the question and they have a good reason for doing it. So again, listen to what they're saying, listen for the reasoning. It's the combinatorial reasoning that's most important here. How did they get their answer? The last section is reasoning about probabilities and proportions. And what they're trying to do with this is take this gumball machine, for instance. This gumball machine has more, apparently it has more yellow than it has red. So if we ask students, which one are you more likely to get? They're probably going to say yellow. But wait, they may also say, well, I can see a lot of the yellow here, but because I can see a lot of the yellow and I know that there is a mechanism down under that that's actually going to serve those up, and I'm going to assume that there's the same number of yellow and red, that means the ones that I can't see are the red ones, which means the red ones are further down closer to that mechanism, and that increases the likelihood that when I turn that crank I'm going to get a red one instead of a yellow one. Again, no wrong, no right answer. Listen for the reasoning. When you get kids that are reasoning like this, the important implication here, when they're reasoning about all of these, in all of these ways, when they're formal operational, the important implication here that we need to remember for both instruction and assessment is that these kids are capable of formal thought. They're capable of working in the abstract, but they're not always comfortable working in the abstract. So what we need to do is we need to begin our instruction and begin our assessment at their level of comfort, which for these kids is probably concrete operational. Then we allow them to move up into formal operational by guiding them with these more abstract applications of the concepts that we're teaching them. If we do that, remember that it's very important for us to match our assessment with our instruction So if we're going to teach kids in the way that we're taking them as a transitional thing from concrete to formal, then we also need to assess them from concrete to formal. That's the important implication of formal operations.